Electronegativity. So in your previous experience, you classified compounds in two general ways. You had ionic compounds and you were taught that was generally result when you had a non-metal bonded with a metal. Okay. And then for molecular compounds, or covalent compounds, you were told they were non-metals only. We were taught that earlier. And ionic compounds also, for completion's sake, could be composed of polyatomic ions. But you weren't really told why. Now, with electronegativity, you can get a knowledge of why. Okay, so what electronegativity is it is a measure of how strongly an atom will pull electrons or electron density to itself. Okay, and the scale is from 0 to 4. Okay, that's the electronegativity scale. Where 4 is the most hungry for electrons, quote unquote, and then towards 0 is less hungry, okay, or the ability of the atom to attract electron density to itself. What you see is fluorine. It's got a 4.0 for electronegativity. It is the most electronegative, meaning that it will draw electron density toward itself over any other element in a chemical bond. The least electronegative elements are the metals, things like francium and cesium. Okay, so that is a value for how hungry an element is for electrons. Now we have a way of classifying, using numbers qualitatively, quantitatively, whether a compound is ionic, molecular, or covalent, or polar covalent, a new category, based on electronegativity differences. So for example, an ionic compound that you've had experience with is sodium chloride, table salt. So in your previous knowledge, you were just told, well, sodium's a metal, chlorine is a nonmetal, it's an ionic compound. Well, now, using electronegativity, we see that chlorine has an electronegativity value of 3.0. Sodium has an electronegativity value of 0.9. And the difference in electronegativity, delta En, is 2.1. Okay, the absolute value, if you subtracted the other way around, but the absolute difference between the two is 2.1. That is greater than this value. So these values, an electronegativity value greater than 1.8 indicates that you have an ionic compound. If you look at molecular oxygen, no oxygen atom is more electronegative than itself, but 3.5 minus 3.5 is 0. So oxygen, molecular oxygen, is an example of a pure covalent bond, okay, because you have equal atoms. Okay. In organic chemistry, you often see many carbon-hydrogen bonds. Okay. Carbon has an electronegativity of 2.5. Hydrogen has an electronegativity value of 2.1. So even though you get a value that isn't 0, but 0.4, that value it's not really a polar bond in that category. Okay. Just slightly. Okay, that 0 points are right on that line. So a carbon-hydrogen bond is the borderline of a pure covalent and a polar covalent bond. It's really not very polar. Okay. But another common bond is an oxygen-hydrogen bond that occurs in organic molecules or just water. .5 minus 2.1 is 1.4. Okay. This is a polar covalent bond. Okay. So it's in between a pure covalent bond and an ionic bond. Okay. It is polar. Then polar bonds often use a notation called delta dagger. Okay. And if you're creative, or maybe not creative, but have a decent imagination, it kind of looks like a dagger, a knife, where the pointed end is always drawn toward the more electronegative atom, and the hilt end, which you would, if you were holding a sword or a knife, the handle end is drawn toward the less electronegative. And then use the lowercase Greek letter delta to show a partial negative charge on oxygen and a partial positive charge on hydrogen. Okay. So it's not an ionic bond in the sense that the oxygen has all of the negative, has a full-blown negative charge, and hydrogen has a full-blown positive charge, but there are partial, smaller charges. This feature is going to be important when you learn about intermolecular forces and how certain organic reactions occur later in your chemistry pursuits. But that is a way of quantifying bond polarity, getting a feel for whether a bond is ionic, pure covalent, or polar covalent.